All right, so this week we're going to take a look at vectors. Okay, I put the section from the book on the board. This is 5.4 if you're in the packet. Okay. And a vector is basically used to describe two things. Right? If I was throwing an object, okay, or you saw a plane traveling in the sky, same idea, and you wanted to describe to somebody exactly how that object was moving, what would you have to describe to someone? Actually, two things you'd have to tell someone to describe how like an object is moving. Tell me the two things. Yep.
Direction and speed.
The direction and the speed. Yep. You'd have to tell me how fast it's going, and you'd have to tell me which direction it's going. Now, speed, we call that magnitude, right? So in that case, if you're dealing with like an object moving, magnitude is speed, and direction could be, it could be up, down, however you describe direction. So that example that I gave with an object moving, that's called a velocity vector. Okay? When you want to describe velocity to someone, there's two things you have to explain. How fast are you going? What direction are you going? Another example is force. And if you've done physics, you might have done some examples with force. So an example would be like if I was pushing down on this front table. Well, there's two things that go into, like if I push on the table, that'll control which way the table moves. How hard do I push on it? And what direction do I push? Right? Pushing down on it with 50 pounds of force versus pushing like left on it with 50 pounds of force. Well, that's two different things. Right? So in that case, the magnitude is how hard I'm pushing on the table, and the direction is, well, the direction I'm pushing on the table. So here's an example with just with airplanes. So this is showing, I think the planes are moving. If you look closely, they move every now and then. Showing the different airplanes that are flying right now, at least like the major, like the bigger ones. And each one of these planes you could think of as a vector. So if we click on, let's click on this one. Now this plane that's over like Mount Greylock right now in the upper left, it's traveling east. When you look at east as a compass heading, that's 90 degrees. So let's look it up and see which way the plane is traveling. And let's see how fast it's going. All right, so it says, let's see, so it's traveling, I don't see its speed. Oh, speed. 565 miles an hour. Okay, so that's part of its vector. Now, the other thing you'd have to think about with planes is, yeah, it's 3D. So it might look like two planes are very close, but one could be on the ground and one could be at 30,000 feet. So we're not really going to get into too much with 3D right now. But the idea is there's its speed, and then its route. Let's click on decode. So that's some computer lingo for the direction it's traveling. I said it's probably going to look like it's traveling roughly 90 degrees somewhere in there. Let's see. So, yeah, right in here. 80, 81, 82, 82. And all of a sudden it like flipped out, went upside down. And then 90, 99, 99, 90. So maybe it had to avoid maybe some bad weather or something. But you can see this plane has several directions. So it was traveling at a heading of 271 degrees. That would be, let's see, 0. That would be west. So it started out going west, and then it tells you how long. So it was going like 75 degrees for 231 miles. And most of the headings here should be between be in like an easterly direction because it's coming from LAX and it's heading to Logan. So that's starting on the west side of the country and heading east and a little bit north too. But we're going to deal with vectors that are a little simpler. They're not going to have this many different direction changes. We pretty much look at a vector that just goes in one direction and it just stays in that one direction. All right? Okay, so any question on that idea? So we got a direction and we have a speed. And for our purposes, we're going to assume the speed stays the same. All right? This plane probably changes speed, as it's taking off and landing, but that's a little more complicated. All right. So all those different planes that you saw, it's the job of the tower near that airport to kind of control all the traffic coming in and leaving. So there's computers that look at all these planes. There's probably some safety margin, so they can't have planes too close. Maybe they can only have one landing every 60 seconds just to keep them a little spread out. I don't know. But all this information is in a computer, and you can think of all these planes as vectors. Okay? All keeping track of all of them. All right? So one way you can represent a vector, and this is good if you're going to draw some things out. We'll do a lot of drawing today, is using an arrow. An arrow is perfect because if you want to represent magnitude, all you have to do is make your arrow longer or shorter. And direction, well, arrows naturally have direction because on the end of it, you put a little point. So it tells you which way it's pointing. Right, so when we draw vectors, we'll draw them as arrows. So visually, great way to start out with vectors because it makes things make a lot of sense, makes it very simple. When you want to start getting into some more calculations with vectors, drawing takes forever, right? Because to do it nice, you need a piece of graph paper, you need something that's straight, it's going to take a while. So we'll start out drawing them, but we're going to get away from drawing eventually, except for word problems. So vectors always have 2 points associated with them, an initial point and a terminal point. The initial point is where the vector starts, and the terminal point is where it ends. So it's kind of like a ray from geometry, but what's the difference between a ray and what I drew on the board? Big difference, yeah?
A ray continues endlessly from the origin point, whereas the vector stops at Q.
Yeah, the vectors stop. Like they don't go on forever. Okay? A ray in geometry, it does. Okay? So since this is a ray, you could use the notation from geometry like this. PQ. We don't really do it that way as much with vectors, but I mean you could, but I'm going to show you a shorter way to do it. Now, this symbol right here doesn't mean that it points to the right. That symbol just means that you have a ray starting at P and heading to Q. Right? If you wanted it to go, let's say you had this, let's say P, Q, and you wanted to write that in your notation from geometry, you'd do this, Q, P. The symbol on the top of the 2 letters always points to the right. The letters on the bottom tell you which way it goes. Start at Q, end at P. Start at Q, end at P. All right. So again, the thing on the top has nothing to really do with the actual direction. And when I show you the way we're going to write vectors, we're going to do kind of the same thing. We're going to put an arrow on the top. But that arrow on the top doesn't really tell you the direction. It just tells you whatever you're writing below is a vector. And we like to use single letters. Okay, when we want to name a vector, we usually use a single letter. Now, where else do we use letters in math besides, we're going to use them for vectors, but they're also used for what? Yeah?
For angles, for sides.
Okay. What are those things in general? Angles, sides. If you use a letter, that's a variable. It's a variable. So that's a problem. How do you write a single letter on paper and know whether that single letter is a variable or a vector? They're 2 totally different things. Well, there's 2 ways you can do it. One way is to put the single letter and put a little arrow on top of it. Again, this arrow does not mean the vector points to the right. It just means it's a symbol that means vector. Okay? It always points to the right in that symbol. Or you can make the letter bold. If you look in your packet, that's how they do it. Okay, they make the letter bold. I think bold works well if you're typing something out. It's very easy to see a bold letter. But on paper, making letters bold kind of can take a while and it might not be super clear. So if I'm writing stuff by hand on paper, a lot of times I'll do it that way. If I'm going to type it, It's easier on a computer to just make a letter bold. Okay, so any questions on the two different symbols you can use to label a vector? The only letters you wouldn't want to use, like the letter O for a vector. How come? Why could that be confusing? Sam?
It could be confused for a 0.
Yeah, if you use any letter that looks like a number, that's going to be confusing. Okay, so we'll just stick with letters that look just like a letter and there's no number that you're confused with them. So. All right. So different things we're going to look at is how we can combine vectors. Okay, today we're going to start out by looking at what happens when you add two vectors together and what happens when you subtract. So let's pretend that we had a box here, okay, and I push up on the box and somebody else pushes right on the box. And let's assume that the strength that we're pushing at is consistent. Like I push it exactly the same amount of power and so does somebody else. Never changes. What would happen to the box? Okay.
It would go up at an angle.
It would go up at an angle. Even though neither one of us would be pushing at an angle, I'm pushing up, somebody else is pushing right. But what's going to happen is those two vectors, those two forces are going to combine together and make a new force, right? A new force that's going to go up into the right. Right? Another way you could think of it is if like a plane was trying to fly north and the wind was blowing west. Well, the plane is going to now go north and a little west because the wind is going to blow the plane off course, unless the pilot corrects for that. Right? So the idea is when you have two vectors, whether they're forces or whatever, and you combine them, you get a new vector. Right? If I had, let's say I had a boat, okay, and I'm on a river. And let's say there's a current in the river. If I'm going with the current, well, I can think of that as a force that's pushing my boat. I can also think of the engine as a force that's pushing my boat. And in that case, they're working together. The current's pushing my boat, the engine's pushing my boat, so now I'm going to go even faster. So I get more force. Okay? Now the opposite would happen if you're trying to go upstream. Current's coming down, you're trying to go against the current. The force from your engine is pushing you upstream, but the current is trying to push you back down. So now your engine isn't quite moving you as fast. That's because the two forces have combined together to create a new one. And that's basically how fast your boat is going. All right? So that's the idea. When you combine two vectors, you get a new vector. Sometimes it's a faster speed, sometimes it's slower. Depends if you're like with the current or against it. And sometimes the direction changes. Like if you were flying in a plane and the wind blew, it would change your direction a little bit. Okay? But the point is, you get a new vector. So what I'm going to show you is how to add two vectors. I'm going to call them V and W. I'm going to add them visually, and then I'll write down the steps after. Very simple idea to do it. It's kind of wordy to explain it, but here's the idea. Let's say that represents vector V. This represents W. If I want to add those two vectors together, this is how you do it. V, W. You line them up just like that. So what I just did is I lined up the end of V, the terminal point of V, with the initial point of W. Put them right on top of each other. And now the final answer is when you connect where you started to where you finished. That vector that I just drew represents V plus W. So if you think of those original vectors as forces, that's what would happen if you combine the two forces together. Right? So again, connect the terminal point of the first one to the starting point of the second one. And then to get the answer, take your initial point for the first one and your terminal point for the second one and connect them in that direction. Right? And I have that all kind of written out here. So line up your vectors the way I just told you. And once they're lined up, it's like you're drawing in the diagonal. From the start point of the first to the ending point of the second. And now you can stack as many vectors as you want together. Okay, I just did 2. But if I had, say I had this one, this one, this one, and that one. And I wanted to add all those together. Well, first I have to break them apart so I can move them separately. Let's try it again. And now I would just connect them all. So it doesn't matter what order you connect them in. And I'll show you that after. So let's take that one, and that one. Oh, like that. The important thing is you have to connect them so the arrows all go the same way. Think of it as like a one-way path. Okay? You wouldn't want to connect something like that. Think of that, that's like a collision. Now you got 2 things coming, that's not right. Right, so I connected them all together, and the final answer, take where I start, take where you finish, and visually, that's the final answer if you combine all of those together. And as I said, it turns out you can put them in any order you want. You'll always get the same answer. Most of the time, we're going to work with 2 vectors at a time, usually not like 4, but you can do it with as many as you have. Okay. Questions on that idea? Okay, so let's add these 2 vectors up. Now, the one thing you got to be a little careful about when you add is you have to kind of think ahead a little bit, especially if you're using graph paper. When I add these up, would I want to start more on the left side of the graph paper or on the right? Because I don't want to go off the edge. About how?
More on the left side.
Yeah, I would start on the left side because the vectors go to the right. So if you start on the right, you're going to run out of room. It doesn't matter where you start. You can put them anywhere you want. But we're going to take V, which is right there, and line it up with W, which is right about there. All right. Now I've lined them up. I haven't actually answered the question yet. So what's my last step? How do I finish that up? Yeah. From the beginning point of V to the end point of W. Yep. And it's important that you do it in the order he said. From the beginning of V to the end of W. Just about like that. And that's the answer for how you add V plus W. There is an arrowhead on that. It looks kind of small, but just make it obvious. And again, these are bold. I did them bold because I can just highlight my font and make it thicker. So that was easy. If I'm drawing it by hand in bold, I got to take time and go like this. If I didn't want to do the bold, what's the other way I could write the letter? Yep, you could put the arrow right on top of it. But don't do both. Do one of them. Okay, any questions on that? Okay, let's look at this one. So now I want to add v plus w. And again, these are bold. Okay, before I do it, does anybody think they see what's going to happen here? It's going to come like, what do you mean it's going to? Yeah, yep.
It's gonna cancel each other out.
Yeah. So what the goal is this. Take the dot in red and line it up with the dot in red. Take the ending point of V and put it with the initial point of W. Once you do that, connect from that green dot to that green dot. So line up the red dots first, and then once you do that, connect the green dots. Well, if you line up the red dots, watch what happens. Put the end of V right at the beginning of W. Now look at the green dots, they're the same. So it's like Sam said, they kind of cancel each other out. But what did I say earlier? Whenever you add two vectors, the answer is always what? Oh, got it?
Isn't it 0?
Well, what did I say? When anytime you add two vectors, the answer is a what? A new vector. The answer here is still a new vector. But it's like they canceled out. So if you did regular addition with numbers and added them, and they canceled out, what would you write? Okay. So if you added numbers together and they canceled out, what would you write?
0.
0. Okay, you would write 0, number 0. Well, we can't write the number 0 here because when you add vectors, the answer is always a vector. But what you can write is this. The 0 vector. Or you could write it this way. So the 0 vector, that's kind of a special example. That's a vector that if you wanted to measure it and find its length, what would the length be? What do you think? Devin?
0.
0. What do you think the direction of it would be? It has no length. How about Ellen? What do you think the direction would be? It's not really a direction, right? The 0 vector, it's kind of weird. It really doesn't point in any direction and it has no length. So it's a special case. So is it even really a vector? Well, yeah, it's called the 0 vector. It's a special example. Every other vector besides that one does have a length and a direction. Okay. Any question on that? All right. So, vector addition. There's a lot of properties that we already know about numbers. Associative, commutative, distributive. You can't assume that anything you already know about numbers works with vectors. Vectors are different. A lot of things do. A lot of things do work. But don't assume because you know 2 plus 3 equals 3 plus 2 that that works with vectors. All right, so what does commutative mean? If I say that like addition is commutative, can someone give me an example of that? Well, yeah.
Maybe you can work both ways.
All right, give me an example. What do you mean?
Like 2 plus 1 equals 1 plus 2.
Yes. Commute, well, without the E on the end, but commute basically means to go back and forth, right? Go from one place to the other. You can move vectors around. You can move them from one place to the other. You can switch their order, and you still get the same answer. That's why I said when I had 4 vectors, and I said you can stack these together any way you want, it's because vector addition is commutative. Okay, I'm going to show you that right now with two vectors. It's kind of hard to draw in your notes. It's really more something you just need to watch on the board. So here's V and W. Okay, I'm going to add them together the way on the left first. I'm going to take V and I'm going to put W on the end. Okay, and I'm just going to draw it by hand, so it's not perfect, but pretty close. Any question on that? Now I'm going to switch it. I'm going to do W and then I'm going to do V on the end. W, V, and I'm going to draw that. And I'm going to compare them. And except I drew it a little curved, but they're pretty much, you can see they are the same thing. Okay? So V plus W, W plus V, the order doesn't matter. Any questions on that idea, commutative? Okay, the other property we're going to look at is associative. Does anybody remember what that one means? It doesn't have to do with the order. The order is going to stay exactly the same on each side. Well, what word do you see in that property? Like a smaller word.
Associate.
Associate. Okay. What does it mean to associate? To what? Do you associate with yourself? Well, I guess you know yourself. But, like, when you normally, like, when you think, you know, you're associating with people, you do it with other people, right? You're associating with people, you're doing it with other people, not just you, yourself, and I. But when you associate, you do that in a group, right? You do it with groups. So that's what associative property is. It has to do with how you group things. And what symbol do we use in math to show groupings? Parentheses. So the associative property doesn't have anything to do with the order. Okay, order is the same. ABC, ABC. But it's what you're grouping together. You're grouping the A and B versus grouping the B and C. And grouping basically changes the order of operations. Changes what you do first. So let's look at an example with three vectors, and I'll show you what happens there. So the way on the left, you do A plus B first. Okay. Here's A plus B. Right, so that's A plus B. And now what does it say to put on the end of that?
C.
C. So I'm going to put C on the end. And kind of starts here and ends right about there. Right. So that's what you get when you do it the way on the left. We don't need that. We're done. You know what else you can do? You can zoom in like a phone. Isn't that cool?
Oh, I still want to message it.
Oh. Just found that out. Although it's kind of hard to do with my fingers. Well, I guess you can kind of do it. But anyway. I just found that out one day. I got excited. All right. So we've got A plus B plus C. Now, on the other side, first I'm going to do B plus C. So here's B plus C. B, put C on the end of it, and draw that in. Because I'm drawing everything by hand, this might come out a little bit more off, but it should be kind of close. All right, so there's B plus C. And now you want to take A and add that on the end of it. So here's A. And now we're going to add B plus C on the end of it. So we start here, and we go right there. So let's see if it's kind of close. Yeah, it's not bad. Isn't that cool? I did pretty good. All right. So all I'm showing you there is that the associative property works. If you change the order you add vectors in, you're still going to get the same answer. Okay. Any question on that idea? All right. So What's the difference between those two vectors, do you think? You have the vector v, and then the vector negative v. What do you think the difference is? We kind of already saw this in this example today. It was example 2. Sam?
I was going to say they're going opposite directions, but
Yeah. That's exactly what happened in example 2. We added two vectors that went in opposite directions. What about the length of the vectors? It'd be the same. It's like measuring the distance from here to the door or from the door to here. You're measuring in different directions, but you're still measuring the same distance. Right? So when you see a negative in front of a vector, it just means the direction is the opposite. Okay? It's like rotating at 180 degrees. If it's pointing up, now it's pointing down. That's the opposite. So negative in front just means to change the direction of a vector. Okay? Exactly 180 degrees the other way. So the direction is different, but they have the same magnitude. So when you combine, like if you were to add those two vectors up, the vector v and the vector negative v, what happened in example 2 when we did that? What did we get? Well, think of them as forces, right? You've got a force that's pushing something to the left a certain amount, and you've got another force that's pushing it to the right at exactly the same strength force. What would happen, Jake? Yeah, they would cancel out. And what did we write down when two vectors cancel out? The zero vector, yes. Is that what I have written right there?
It is. No, it isn't.
It isn't.
You just have 0.
I just have 0. That's wrong. That's impossible. You can't add two vectors and get a number. Now it's good. You add two vectors and you get a vector. Bless you.
That's true.
Okay, so I forgot the arrow. Either put the arrow or make it bold. One or the other. So now, what does this kind of look like? What operation? I mean, it's addition, but it's kind of like subtraction, right? So if you want to subtract two vectors, this is how we're going to think of it. Right? Think of it like, let's say you wanted to do this. Let's say somebody didn't understand how to do subtraction, but they understood addition, even addition with negative numbers for some reason, but they just don't quite get subtraction. So how could you explain that to somebody? You say, all right, well, just think of it as addition. If they didn't like it as 2 minus 3. Yep?
Negative 3 plus 2.
Okay, how about let's keep it in the same order to keep it even simpler. Because then they might say, why'd you switch the order?
2 plus negative 3.
Yeah, 2 plus negative 3. So if you want to subtract two things, all you really have to do is add the opposite. Okay? If you don't get subtraction, all you have to do is add the opposite. That's why when you have something like this, and you say, well, isn't there an easier way to write minus a minus? Sure. Take 4, and then add the opposite of the second number. Well, the second number is negative 5. The opposite of it is positive 5. That's why minus a minus cancels out, because you can add the opposite. And that's how we're going to subtract two vectors. Find the opposite of the second vector, and then add. Now, what does that mean again? If you have a vector and its opposite, what's the difference between the two?
Direction.
Just the direction. So all you have to do to find the opposite of a vector is spin it around 180 degrees. Make it point the other way. That's it. And that's the easiest way to visually subtract two vectors. Don't think of it as subtraction. Think of it as adding the opposite. Then you can use the same steps I already gave you. So now we'll try an example of that. Okay, I want to find v minus w. how am I going to think of v minus w? Since I don't really have a way to do subtraction of vectors, I only know how to do addition. So how can you rewrite that as an addition problem? V plus negative w. V? Yep, I got it right there. But I'm missing something. What vector am I missing that I need? I need negative w. Now, all it's going to do is point the other way. But I can actually do it like exact like this. On this board, I can make a copy of it by going like that. And then if you flip it horizontally and then you flip it vertically, that's the same as rotating 180. I just don't have a button that says rotate 180. So now I have negative w. Now from here, just do what we did before. Take v, add negative w to it, so you're really subtracting, and then draw your final answer. V, negative w, and that's on the top is v minus w. I'm just going to separate it off so you can see it. Right there. And that's your answer. Okay. Questions on that? That's how you do subtraction. Okay. All right. Third operation we're going to look at is scalar multiplication. What does it mean to scale something? Like if you're showing someone your cell phone and they can't see what's on it, so you make it bigger, you make the screen bigger so Jake can see it. Yeah?
You change the size.
You what?
You change its size.
Yeah, you change the size. So what's two ways you can change the size? A couple things.
Zoom in as well.
Okay, zoom in, it would get bigger. Or if you zoom out,
Get smaller.
it would get smaller. All right? So there's two of the things that can happen. So when you multiply a vector by a number, like this, 3v, that's what a scalar product looks like. This is a number, but we normally call it a scalar. It's a scalar times a vector. So the result here is a new vector. In this particular, this one would be a vector 3 times as long as the original. What would that really mean? Well, if it was an airplane or something traveling, it would mean that the airplane is going 3 times as fast. So putting a number in front can make the vector longer, could make it shorter if you put in like 1/2 v. You can also do one other thing. What other kind of number could you have in front? A negative. And what would happen if you put a negative in front? We just did that. It would change the direction. So that's the 3 things that can happen. A scalar can make the vector shorter, if it's a fraction, like 1/3 or 1/2. It can make it longer. Or it can reverse the direction. That's the only way it can change it. It can't arbitrarily change the direction to any direction. It can make it point the opposite way. What?
You used a big word.
I used a big word?
I don't know what that means.
Arbitrary.
Arbitrary?
Yeah.
How about random?
Okay.
Okay.
That's better.
The vector cannot just point in any random direction. It can either point the way it's pointing, or a negative can make it point exactly the opposite. But that's the only direction change it could make. Now, usually we don't scale a vector by 0, because if you do that, then you wipe the vector out. There's no more magnitude, there's no more direction. The answer would be the 0 vector. Okay. Okay. So here they want us to find 2v and a half v, and they've given us what v is to start. Now, using the smartboard, how could I get 2v exact? Not an estimate. I don't have a ruler handy, so how could I get exactly 2v. Yeah.
Would you copy it and then make one line that's the length of both of those put together?
Yeah, just make 2 copies of them, put them together, done. That's 2v. So that one's easy to do as an exact answer. Now, half v, I can't, I don't really have a way to do that one because I'd have to shrink it by 50%. So I just have to kind of estimate where halfway is. Maybe about like that. Notice in both of these cases, did the scalar change the direction? No, because what kind of number is that?
Positive.
It's positive. Yeah. Okay. Let's look at this one. Negative 1v and negative 1/3 v. All right. So when we compare the lengths of negative v and v, how are their lengths going to compare? They're going to be the exact same length. So this negative 1 isn't really scaling it in terms of making it longer or shorter. All it's going to do is flip the direction. Okay, so for that, we can do it just the way I showed you earlier. Do a horizontal reflection and a vertical reflection. Let me try again. There you go. And that's negative v. Now, what about negative 1/3 v? What's going to happen there? Yeah, 2 things. The negative causes it to change direction from the original, and it's 1/3 as long. Well, I already got the direction from up above, but now I need it about 1/3 as long, so I'm just going to estimate maybe that's about 1/3. If you're using graph paper, then you could do it exact. Any questions on that? Okay. All right, so let's just do the second one. 2v minus w plus u. Am I missing anything, any pieces to make that second vector? Yep. So I can make 2v, yeah, let's do that first. So I can go like this and go like that. All right, so I got 2v. Now what do I need? Yep.
The minus w.
I need the minus w. Okay, so this time I'm just going to go like this. So there's minus w. Points the other way. Now, I probably didn't start out in a good spot because minus w goes up and u goes up. I'm going to go off the page. So I probably should have started it a little lower. Not a big deal if you're using a computer to do it, but if you're drawing it by hand, that's kind of a pain. So this is one reason why adding them and subtracting visually, it's not always the best. All right, so there's 2v. There's minus w. And what do I need to put onto the minus w?
U.
U. Let's put that. And there we go. And now connect where you started to where you stopped. Start to stop. And that's the answer. 2v minus w plus u. Questions on that? All right, now let me just move this for a second so you can kind of see something. If I wanted to know the length of that, like how long that line segment is, it's on an angle. It's not straight. Like if it was just like this, that'd be easy. All you'd have to do is count how many blocks. But what shape do you think I could make out of that that would allow me to figure out how long it is?
Triangle.
Triangle? Like this?
Perfect.
Yes, that's what you do. You're good. No, it's not good. So I heard Jake say something else.
The right triangle.
Yeah, right triangle.
No.
Well, that's okay. I drew it a little longer than I did. It's okay. Don't tell me how. So
Just sabotaging it.
you can make your right triangle, and then it's very easy to find the length of the bottom. 1, 2, 3, 4, 5. Height, 1, 2, 3, 4, 5, 6, 7, 8, 9. How could you find the length of that vector? Yeah. So when we get into the length tomorrow, it's just a Pythagorean theorem. We're not going to do the length right now, but you could. What we are going to talk about is the symbol for the length, or the magnitude, and that's when you put 2 bars around it. Okay, they don't use a single bar because we already use that for absolute value. But when you see a vector and double bars around it, that means they want to know the magnitude of the vector. Now, because magnitude measures length, length can't be negative. Like, even if you measure something that goes south, it's still positive when you measure it. Okay? So even if it goes left or down, magnitude is always a positive number. So the next question, I've kind of asked you guys this a couple different ways already, but I'm going to ask it one more time. What would be the difference between those two? Like if you wrote down the answer to the one on the left and the answer to the one on the right. The answers would be opposites?
Yeah.
Okay. Any other thoughts?
Nothing.
Why nothing?
No difference.
Because it's still the same distance.
Yeah. Here, you're measuring a distance. Here, you're measuring a distance. It's like here, you start where I'm standing and measure towards the door. Here, you start where the door is and you measure towards me. It's the same thing. It's just measuring a different direction, but it's still the same thing. So those two things are the same. What is different about them? Their lengths aren't any different, but if you just look at the vector inside, it is pointing opposite directions. One's going like this, one's going like that. But they are the same length. All right. Now, if the vector comes out to a certain length, it has a special name. When we did the unit circle, what was the radius on a unit circle? There's a special number, easy to work with. 1. So if this vector comes out to a length of 1, it has a special name. Does anyone have a guess what the name would be? I just gave you a hint. Yeah?
Unit vector.
Unit vector, yes. So if a vector comes out exactly 1 unit long, it's called a unit vector. So this section has a lot of vocabulary in it. It has a lot more vocabulary than any other section for the rest of the week. Terminal point, initial point, magnitude, direction, unit vectors, there's a lot of different terms. Scalar product, things like that. Any question on that definition? Because we're gonna talk more about unit vectors tomorrow. All right. So drawing vectors is fine, but if we really want to start to be able to do things faster, drawing is going to take all day. You got to have a piece of paper. You got to draw nice straight lines. It would be much easier if we could just represent vectors as numbers. Right? Just do a simple calculation with numbers, not have to draw anything at all, other than writing numbers down. All right? And there's 2 ways that I'm going to show you how to represent vectors, besides actually drawing them out. The first way is called algebraic notation. And I'm not sure why they call it algebraic notation, because usually when you call something algebraic, it means there's a letter in it. This has no letters at all. An algebraic vector looks like this. There's no letters in that at all. So, in general, these 2 will always be numbers. I'm just showing it to you in general. The first one and the second one, those are called your components of your vector. And I already kind of showed you guys components earlier. The horizontal and the vertical components. Okay. I'm going to come right back to this, but I just want to go back to the page where we drew that triangle with the Pythagorean theorem. This, in green, that's 5 units long. That is the horizontal component of that vector in black. This, in red, is the vertical component of that vector. If you take the green vector and the red vector and combine them together visually, you get the black vector. So, horizontal component of 5 and a vertical component of 9, you would write it like this. That vector in black is the vector 5, 9. And I'm gonna write that out right here. So what you can do is think of A and B as like directions. They tell you from a starting point, from an initial point, how many units left and right, and how many units up and down you have to go to get to the terminal point. So yeah, I'll come right back to that. If you look at this one, 5, 9, that tells you start somewhere, go 5 units right, go 9 units up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Draw your vector. There it is. That's the vector that I just had in black. So the 5 and the 9 are like directions, horizontal and vertical. A is the horizontal. If A is positive, you go right. If A is negative, you go left. Just like a coordinate. B is the vertical. If B is positive, you go up. If B is negative, you go down. Okay, so A and B are directions from the initial point to the terminal point. And it is important that you put these angled, I won't keep circling it, but it's important that you put those, let me get it back, that you put those angle brackets on it. Okay? If you don't put the angle brackets and you put parentheses, what would that be? If you put parentheses with 2 numbers between them and a comma. Wouldn't be a vector. That's a point, that's a coordinate. Okay, so you've got to put those brackets on them. So again, A is the left and the right. If you really want to spell it out, A is horizontal. B is the up and down, which means it's the vertical. Okay, so here's another example of a vector, the vector 2, 3. So it tells me how far to go horizontal, tells me how far to go vertical, but what doesn't that tell me?
Where to start?
Doesn't tell me where to start. Doesn't tell me where I should put it. Doesn't matter where you put it. Put it anywhere you want. You could start here, 2 right, 3 up. It's good. You could start here, 2 right, 3 up. Doesn't matter where you put it. But there is a place that is more common than others to start from. Where do you think the most common place to start from is?
The origin.
The origin. Start at the origin, 2 right, 3 up. Okay. You could start here, 2 right, 3 up. But the origin, that's usually the preferred place to start. Okay. If your vector starts at the origin, that's called a position vector. Okay, so if you've got a vector with its initial point at the origin, that is called a position vector. Okay, so the last thing we want to be able to do is figure out a position vector if the initial point is not at the origin. Okay, and I'm going to do that, I'll do it with the one actually I just drew on the other page. Let's take a look at that. Okay, so let me get rid of all these other ones. So if they want you to find a position vector, the only thing they'll give you is the coordinates of where it starts and where it stops. What is this coordinate? Yep, 5, 3. That's my initial point. Where's my terminal point? 6. Yeah, 7, looks like 7, 6. Now, we already know the answer. You wouldn't be given that. But the answer is 2, 3. Does anybody see what you can do with those coordinates to somehow get the answer 2, 3? Subtract them. Which order? Should I do the terminal minus the initial or initial minus terminal? Terminal minus initial. 7 minus 5 gives me 2. 6 minus 3 gives me 3. So that's how you do it. Terminal minus initial. All right. So I'm going to write down what you just said. All right. So suppose you've got a vector, and they'll tell you the initial point and the terminal point, just like I did on the other page. P1, P2. Now, if they don't tell you which one is which, just assume that P1 is the initial, P2 is the terminal. Always. To find the position vector, you want to subtract terminal minus initial. Do it for the x's, then do it for the y's. Just like we did right here. 7 minus 5, 2. 6 minus 3, 3. So there's your formula. Terminal minus initial for the x's. Terminal minus initial for the y's. And since it's a vector, remember you're finding a vector, put those brackets on it. So now you should have a way to find a position vector. You shouldn't have to draw anything. Does everybody have the formula to find a position vector? So let's go like this. Okay, so let's find the position vector between those 2 points. Now they didn't tell you which one was P1 and which one was P2. So when they don't tell you, which one did I say to always assume the initial one is? No, not the smaller one. The first one, yeah, P1. P1 is your initial, P2 would be your terminal. All right, so let's set it up. We're going to have a little arithmetic. When you get to that step, you want to simplify it, but let's just start by filling in the formula. What am I going to put for the 2 numbers in the first part of my vector? What minus what? Yep.
4 minus negative
4 minus negative 1. So that's going to give me 5, comma. And what are going to be the last 2 numbers I subtract? 6 minus 2. And that's going to give me 4. So this vector has a horizontal component of 5 and a vertical component of 4. So if you wanted to start at the origin and draw it, go 5 right and go 4 up and stop. That's how you'd sketch it. Okay, any questions on that? Okay, so that's the first part of vectors. Today we did section 5.4 in the packet. Tomorrow we're going to continue on with section 5.4. Okay, so the homework, make sure you write down the directions. 1 through 10, that's all. 14 to 22 is just the evens. 26 to 32 is also the evens. But don't do what they're asking you to do in the book. We haven't done that yet. All I want you to do on 26 to 32 is find the position vector. Again, if you read the directions they're giving you, it won't make sense. Okay, so just use my directions. And remember, that's in the packet. This is not in your textbook. Okay.